after we learn how to draw this frequency response plot. So basically what we want to do is, at the end of this, we want to project the time domain performance of the system based on this frequency response analysis. We are not living in frequency domain, we are living in time domain. So this is a very important statement that you need to remember. To conduct a frequency response analysis does not imply that the system will be subjected to only a sinusoidal input signal. Probably once in a while, your input is going to be sinusoidal. But conducting a frequency response analysis, so we are just using the information from this frequency response analysis, okay, to project. So here, rather, from the frequency response studies, the time domain performance can be projected. So in the end, at the end of the day, we want to project or design our controllers so that our time domain specification will be met. So that is at the back of our mind. Okay, so now let's continue our discussion. So far, we already know how to draw this frequency response plot. So we use the polar plot. We need the frequency ratio. Frequency ratio is going to give the magnitude. The magnitude of the transfer function is going to give us the frequency ratio, and the phase angle is going to give us how far further away that the output is going to lag the input. So in general, it's going to be called the frequency response plot. But today we are going to talk about the Nyquist diagram. So the polar plot of the frequency response function is known as the Nyquist diagram when the open loop transfer function GH of S is used to generate the polar plot. So when we use this open loop transfer function GH of S, the name given to that plot is called the Nyquist diagram. In general, it is just called the frequency the polar plot of the frequency response function. So what do we get out of this Nyquist diagram? From the Nyquist diagram, we can determine whether the system is stable or not. Okay, and then we can know also this relative stability. Not only that we can know whether the system is stable or not, we can also know how close the system is from being unstable. So that is called the relative stability of the system. From the Ruth table, we can know whether the system is stable or not. But here, in addition to that, we can also know how far or how further away we are from instability. So first of all, so how do we know from the frequency response plot from the Nyquist diagram whether the system is stable or not? So we look at this point -1 on the, where the hell is that? So you look at this point -1 from the polar plot or from the complex plane diagram. See, this is -1. So this is point -1 from this plot. When you plot the Nyquist diagram, so you get this red line when frequency start increasing from 0 to infinity. If the -1 is on the left of your Nyquist diagram, when you cross this real axis here, so the system is going to be stable. So this diagram, if your Nyquist diagram crosses the real axis to the right of -1, then the system is stable. So here the system is stable, but when the Nyquist diagram crosses to the left of -1, so now you know that the system is now unstable. This is the system is unstable. What the hell is this? Go away. Close that. Okay, so that is how you know whether the system is stable or not. You just look at this point -1. Now, what about this relative stability? How do you know whether the system is almost unstable or whatever? But if your Nyquist diagram goes directly through point -1, and then there is, now you know that the system is marginally stable. Okay, so to the right of -1 is stable, to the left of -1, so this is unstable. If the Nyquist diagram go directly through -1, then you know that the system is marginally stable. So relative stability, we can only talk about relative stability for a stable system. There's no point of talking about relative stability if the system is unstable in the first place. So when you want to talk about relative stability, we need to go to a stable system. So for a stable system, we can now evaluate the relative stability. Okay, so let's evaluate the relative stability. So the relative stability is measured using the phase margin and the gain margin. So what is the phase margin and the gain margin? Now consider this Nyquist diagram for a stable system. Imagine that, so this is now a Nyquist diagram for a stable system. Now, the frequency is going to change from 0 to infinity. So this is frequency from frequency equals 0. So there is frequency infinity. Now, there are two frequencies that you need to be aware of. So the frequency when the phase angle is plus and minus 180. So that is called the omega p, which is known as the phase crossover frequency. When the phase angle is equal to plus or minus 180, that phase angle is known as the phase crossover frequency. There's another frequency that you need to know, is omega g. It is called the gain crossover frequency. The gain crossover frequency is when the magnitude is equal to 1. So you draw a circle of radius 1 around the origin. The frequency where the magnitude is equal to 1 is called the gain crossover frequency. Let me go through again. So you start with frequency equals 0, and then you increase that to infinity. Along the way, you are going to meet gain crossover frequency. Gain crossover frequency is when the magnitude is equal to 1. And then after that, you're going to meet another frequency called phase crossover frequency. Phase crossover frequency is when the phase angle is plus and minus 180, and then you go on and then until frequency is equal to infinity. So that is some definition of frequency along the way. So how do we evaluate this relative stability in the form of phase and gain margin? Okay, so you draw a phase margin gamma is that angle when you draw the circle of radius 1 from the origin, and then so this is the gain crossover frequency. So you draw a line to the origin, so that angle is known as the phase margin. See? So when phase margin is getting smaller and smaller and smaller, you know that the system is getting closer and closer to become unstable. A large phase margin, system is more stable. A smaller phase margin, the system is become closer to unstable. When the phase margin is equal to 0, when that angle is equal to 0, so you are exactly at that point, so -1. So when phase margin is equal to 0, so you are already marginally stable, one step away to become unstable. So there is the phase margin. And what is the gain margin? So the gain margin is evaluated as using the magnitude at phase crossover frequency. The magnitude at gain crossover frequency is equal to 1, this is by definition. But here to evaluate the gain margin, so you need to know the magnitude when the phase is equal to phase crossover frequency, which is x. X here is the magnitude when frequency is equal to phase margin. So the gain margin is just 1 over x. So you can imagine now, when x is larger than 1, when x is smaller than 1, so you have your stable system. When x is equal to 1, so your system is now marginally stable. So 1 over x is called the gain margin. Okay, so phase margin is gamma, the angle gamma. The gain margin is 1 over x. So if x is equal to 1, if the gain margin is equal to 1, then your system is marginally stable. Any value of gain margin greater than 1, your system is stable. Okay, so when your x becomes smaller, gain margin is going to be greater. So gain margin greater than 1, your system is stable. When your gain margin is 1, you are already marginally stable system. Right. So that is how you evaluate gain and phase margin. So here are some definition again. So omega p is called the phase crossover frequency. So when the phase margin is negative 180 or positive 180, the frequency at that particular time is known as the phase crossover frequency. The gain crossover frequency is when the magnitude is equal to 1. So this is just by definition, the magnitude of the Nyquist diagram at gain crossover frequency is equal to 1. This is just by definition. All right, so that is how we evaluate the gain and phase margin. So when you draw the Nyquist diagram, so the omega is from 0 to infinity. There's a lot of points to be to choose from. How do you make sure that the distribution of your point is well distributed? See, there's a lot of points from 0 to infinity. How are you going to choose the point? Are you going to choose from 0, 100, 200? How do you get to infinity? So there is a guideline here, a guideline that you can use. So a good Nyquist diagram can be obtained when the frequency range is chosen properly. You need to choose properly, otherwise your distribution of point will not be well distributed. You need to choose it properly. How do you do that? So as a guideline, the range of frequency is chosen such that the minimum frequency that you need to look at is 1 over the maximum time constant, and the maximum frequency that you need to look at is 1 over the minimum time constant. All you need to do is determine the maximum time constant and determine the minimum time constant. At least that 2 points you must compute a point where you want to plot your frequency diagram, and then after that you can choose a few more points around this minimum frequency and maximum frequency. Now let's go back to our objective. See, the objective is to project the time domain performance. How do you do that from this the whole thing that we have discussed? Okay, so there's a good Nyquist diagram. So we select this point. Okay, so this is some guideline that give you the design, how you can design your controller properly. So here, for satisfactory time domain performance, the system is designed such that you want the gain margin to be between 2 and 3. So if your gain margin is between 2 and 3, so that can be considered a good, satisfactory control system, or the phase margin between 30 and 70 degrees. As long as you fall within this point, and therefore your controller is doing a good job, or some people say that you will have adequate damping. So so here, when the gain margin is equal to 1, there is already the system become unstable. You want it to be bigger than 2. So when your phase margin is 0, so that is already become unstable. You want it to be bigger than 30 degrees. And you don't want gain margin to exceed 3. That's going to be, your system is going to be, your response of the system is going to be very slow. You want the response to be fast enough. So therefore, you don't want to exceed 70 degrees for your phase margin. You don't want your gain margin to exceed 3. But this is just a guideline. You want to fall somewhere in the Goldilocks zone, not too hot, not too cold, just the right temperature. All right, so there's a story behind the Nyquist diagram. But okay, so let's go into detail of the problem. Okay, all right, so let's look at example 4.8, for example. So now here, this is a typical question that you are going to face in your test. Oh, by the way, there's always one question in your test about frequency response analysis. There's another question in your test about, in your final exam, about frequency response analysis. Most of the time, Nyquist diagram will be asked in your second test. So you can earn 10 marks out of it. And then in the final, probably there's another question on frequency response analysis. You are going to draw the boat diagram. So the Nyquist diagram is going to be asked in your second test. I guess it's going to be soon. Yeah. So this is a typical question that you're going to face in your second test. So here, draw the Nyquist diagram for the control system shown below. So here you are given this control system in a form of block diagram. Probably the controller, the proportional gain controller has been chosen for you. There's 10 there. It is already factored into the block. So the first task is draw the Nyquist diagram for the controller system shown below. If the system is stable, see, determine the gain and phase margin of the system. A simple question like this probably is going to earn you 6 marks from your test. Just draw the Nyquist diagram and compute the gain margin and the phase margin. Right. So what do you need to do to draw the Nyquist diagram? See, the Nyquist diagram, you need to extract the open loop transfer function. That is your first job. You need to obtain the open loop transfer function, which is GH of S. Remember that. When you want to draw the root locus, you also need this open loop transfer function. See, in your test, don't you ever obtain the closed loop transfer function to draw the Nyquist diagram. Don't you ever obtain the closed loop transfer function to draw your root locus. So you just need the open loop transfer function, GH of S. So basically your feedback loop is just 1. So this is already your open loop transfer function. So you get this open loop transfer function, which is 10 divided by S, and the second factor is 1 plus 0.2S, and then 1 plus 0.05S. So this is already the open loop transfer function. Do not obtain the G divided by 1 plus GH, which is the closed loop transfer function, to help you draw the Nyquist diagram. Some of you may do that, but okay, just don't do it. Just don't do it. Okay, so to draw the frequency response plot or the Nyquist diagram, all you have to do is replace S, the Laplace variable S, with omega, with j omega. Replace S with j omega. So you have now 4 factors: 10, 1 over j omega, 1 over 1 plus 0.2 omega j, 1 plus 0.05 omega j. Now this is now in the form of complex number, j omega. So so for a complex number, you're gonna have a magnitude as well as the phase angle. So you're gonna compute the magnitude for all frequency from 0 to infinity and the phase angle from 0 to infinity. Okay, so the magnitude of this open loop transfer function, 10 is just 10. The magnitude of 10 is 10. The magnitude of j omega is just omega. It's in the denominator, of course. 1 plus 0.2 j, 0.2 omega j. It is, so now you have the real part and the imaginary part. So the magnitude of that is the square root of the real part square, which is 1 square still 1, and then 0.2 omega square. So there is the magnitude of this, the factor here, the second factor in the denominator. Your third factor in the denominator, the magnitude is square root of the real part square plus the imaginary part square. So this is your expression for magnitude of this open loop transfer function. Now the phase angle, you have 4 terms here. In the numerator, you have 10. It's just a real number. The phase angle for real number is 0, so you don't have to worry about the phase angle of 10. So the phase angle of 1 over s here in the 1 over s, or since it's in the denominator, you put a minus sign. Every term in the denominator, you put a minus sign. So omega is just the angle of omega is always 90 degrees. So the minus sign comes from the fact that it is in the denominator. So you can use arctangent to compute the angle, the phase angle of the second term. So the negative signs come from the fact that it's in the denominator. Arctangent of the imaginary part divided by the real part. The real part is just 1. So divided by 1 is no different there. Now here is again repeat the same thing for the third term. Term here. So the negative comes from the fact that it's in the denominator. Arctangent of the imaginary part divided by the real part. So the imaginary part is 0.5 omega divided by 1. Now you need to compute g of h for all values of omega from 0 to infinity. You need to compute the phase angle for all values of omega from 0 to infinity. Now comes this handy guideline here, because now you want to choose the value of omega from 0 to infinity. So you need some guide how to choose the value of omega. So you need to know the maximum time constant and the minimum time constant. So the time constant is, you can get this from, this is 1 plus ts. So this is the time constant. The minimum time constant is 0.05. The maximum time constant is 0.2. Okay. So we need to compute that. So the range is selected using this. The maximum time constant is 0.2. The minimum time constant is 0.5. Where do you get that? So this is just here. So this is 1 plus ts, 1 plus time constant s. So the maximum time constant is 0.2. The minimum time constant is 0.05. So 1 over that. So the minimum omega you should look at is 5. 1 over 0.2 is 5. 1 over 0.05 is 20. At least you must compute the magnitude and the phase angle for these two frequencies, 5 and 20. And then to make a good diagram, you just select a few more points. Okay, so now at least you must compute for this omega is equal to 5 and omega is equal to 20. And the rest you just select. I just select here, just randomly